but now we're going to delve even deeper into them, and we're going to try to eventually solve them. So we won't just be solving things that are to the second power or to the third power. We'll be able to solve equations that the highest exponent is 4 or 5 or 6. Okay? So some of this we've actually already talked about. Degree of a polynomial, we've talked about. This is a refresher as to what a degree of a polynomial is. We've also already talked about what the leading coefficient means. So this is a review so that when I use these two vocab words, you actually know what we're talking about. So does anyone remember what the degree of a polynomial is? No? Yeah, it's the exponent. It's the highest exponent. So you look at all your exponents, and whatever exponent is the highest is your degree of the polynomial. Okay, what would be the leading coefficient then? What does the word coefficient mean? The number in front of the variables are all coefficients. So the leading coefficient is going to be not necessarily the first one, but the one that's attached to the highest exponent. So it's the number attached to the highest exponent. I mean, if our polynomial is written in the correct order, it would be the first one, but they're not going to be for this first part. So for these two functions, we want to find the degree of the polynomial and then the leading coefficient to go with it. So for number 1, we've got 7x to the 6th minus x cubed minus 1 over x. So we have to look at all of our exponents and figure out which one is the highest. So 6 is the highest here. So for this first problem, we have a degree of 6. And what's the leading coefficient then? 7. So the leading coefficient is 7. And leading coefficient, I usually just abbreviate as LC. Is that okay? Okay, so second polynomial, we have 1/2 x squared plus 2x cubed minus x to the 5th. So what would be the leading coefficient? Yep, so just the 5. Oh, sorry. What's the degree? The degree is the 5, and then the leading coefficient is, it's not just 1 though, because there's a minus sign there, so we'd say it's -1. So here's our highest exponent, the negative x to the 5th. So the degree is 5, and the leading coefficient, the value in front of it is -1. Is that okay? Actually, by knowing those two pieces of information, you should, by the end of this chapter, be able to graph it. Give a rough sketch of how it looks like, just with those two pieces of information. And we're going to start seeing how that's done today, but we won't actually start graphing them ourselves until later on. All right, so we're going to evaluate for a little bit. We have to remember how to do this as well. This is also a review. This is stuff that we talked about earlier on in the year. We need to make sure we come back to it, and so we remember it, because these are all things that we have to use throughout this chapter. So here I have f of r, so it's a function of r, is equal to 3r squared minus 3r plus 1. We want to find f of 1, f of 2, and f of 3. Who recalls how we can find those values? Yep, plug the 1 in for the r is. So if we want to find f of 1, every time we see an r, we plug a 1 in. So this is 3 times 1 squared minus 3 times 1 plus 1. Well, 1 squared is 1. 1 times 3 is 3. So this is saying 3 minus 3 plus 1. So what's f of 1 really? Yep, so f of 1 is really 1. Okay, we want to find f of 2, so we can do the same thing, f of 2. So instead of the r, what do I write down this time? 2. So f of 2, I have 3 times 2 squared minus 3 times 2 plus 1. 2 squared, 4, so 3 times 4 is 12, so this is 12 minus 6 plus 1. So f of 2 is 7. Make sense? All right, f of 3. So this time, instead of the r, I'll plug the 3 in. So we'll say 3 times 3 squared minus 3 times 3 plus 1. So 3 squared is 9 times 3 is 27. So 27 minus 9 plus 1. What is this? 19. Is that okay? Okay, so that's just finding it with our numbers. So now, number 4, we're going to find it with expressions. So we're not just going to evaluate and get one number out, we're going to evaluate and get an expression out. So here we have p of x. So this is a function called p of x. Is equal to x squared plus 3x plus 4. We're going to find p of a squared and p of a plus 1. So what do you think we should do to find p of a squared? Instead of having x's in our equation, what should we replace them with? Yep, the a squareds. So every time we see an x here, we're going to replace it with an a squared for this one. So p of a squared would be a squared squared plus 3 times a squared plus 4. We have to simplify that. So a squared squared, what does that give us? Yep, a to the 4th plus 3a squared plus 4. So that's our p of a squared. Is that okay? Okay, we're going to do it with one other one. We're going to find p of a plus 1. So this time, instead of x, I have to plug in an a plus 1. So p of a plus 1 is equal to, instead of x squared, we would say a plus 1 squared plus 3 times a plus 1 plus 4. How will I simplify the a plus 1 squared? Yeah, when we do a plus 1 squared, there's 2 of them. So it's like taking a plus 1 times a plus 1. So we have to make sure that we FOIL that out. So we don't want to forget about the outside and the inside there. So when we combine a plus 1 squared, what do we end up getting? A squared plus 2a plus 1 for the last. A squared is our first term. Our outside is plus a. Our inside is plus a. So plus 2a when we combine. Our last is plus 1. What should we do with the 3 times a plus 1? distribute, so plus 3a plus 3. Then we still have the plus 4. Yep. Now just combine all your like terms together. So here we have p of a plus 1 should equal, yep, a squared plus, yep, 5a plus 8. Good. Like I said, that's all stuff we did at the start of the year as well. We did those types of problems, so it is coming back and revisiting it. How we got the 2a? Yeah. We foiled these two together. We skipped the middle step because we should be able to do that. So first is a squared. Outside is plus a. Inside is plus a. Last is 1. A plus a is 2a. So we did the middle step in our heads. All right, so is that okay? All right, so that's all review. So now we're going to get into looking at these graphs and a little bit newer stuff. So we're going to talk about end behavior. Yeah, that's great. I'm teaching. Right. We're going to take a look at 4 different graphs. And we're going to be able to tell quite a bit of information about the end behavior because of it. So these are just 4 different shapes of graphs. No big deal. And we, based off these shapes, we're going to just describe where the ends of the graph are going. And we also will be able to tell what the leading coefficient is and the degree of the polynomial as far as if it's even or odd. So we're first going to talk about end behavior. These are our 4 general shapes of the graph where our ends are. Okay, so just focus on where the ends of the graph are. So this first one to the upper left here, both the ends are facing upwards. Okay, we can have a graph where the ends look like this, where both of our ends of our graph are going up. We could have a graph where both of the ends of the graph are going down. What do these 2 graphs resemble? We did them. Parabolas or quadratics. These kind of look like quadratic graphs. Okay. And then we could also have graphs where our ends are going off in the opposite direction. So here, this end is going up and to the right on the right-hand side, but then on the left-hand side, it's going down. Okay, and the other one's just reversed. So we're going to describe what the end behavior is doing. So to describe what the end behavior is doing, we are going to use f of x approaches, and we're going to fill in where the end behavior is going. F of x, remember, just stands for our y. So when you see the f of x, think of that as your y direction. So we want to know where f of x goes as x approaches infinity, so a positive value. And then we want to know where f of x goes as x approaches a negative infinity, so to the left-hand side. That is the way how end behavior is always set up. Every single time it's set up this way, you just need to fill in which way your y direction is going. On the right-hand side of the graph, so the infinity side, and on the left-hand side, so the negative infinity. So for this graph, f of x is going towards which way as x goes to infinity? Infinity is positive, so which way are we ending our graph on this right-hand side here? Are we going up or are we going down? We're going up. So do you think up is positive infinity or negative infinity? It's positive, so we're going to fill this in with a positive infinity. Okay. Now you do the same thought process for the left-hand side of the graph. So for the left-hand side of the graph, where is that end going? Up. So we're going up over here. So then that we also would fill a positive infinity in. Is that okay? So we're going to do this for these 4 graphs. We're going to write the end behavior out for these 4 graphs. So the outline for it is always the same. The 2 values that change are what f of x approaches. So for this next one, f of x approaches something as x goes to infinity, and f of x approaches something as x goes to negative infinity. And the little arrow just is standing for going towards. So as our graph is heading towards that number, where is it heading towards?
So is there always going to be a negative and a positive infinity even though the arrows aren't pointing?
In your x direction, yes. The positive infinity for the x direction is standing for the right-hand side of the graph. And the negative infinity on the x direction is standing for the left-hand side of the graph.
Oh, yeah.
Think about your graph, how we graph things. So in this case, for the second graph, what's happening to our ends? So as x goes to positive infinity, so the right-hand side, where are we going? Yeah, we're going to negative infinity. We're going down. And then on the left-hand side of the graph, where are we going?
Down.
Also down, so negative infinity. Is that okay? All right, so let's do these last 2 as well. So f of x approaches what as x goes to infinity, and f of x approaches what as x goes to negative infinity. Okay, so as x is going to positive infinity, so the right-hand side of this graph, where's our end going? To positive infinity, because it's going up. And then as x goes to negative infinity, so the left-hand side of our graph, where are we going? Down, so negative infinity. Making sense? Okay, I'll do the last one, and then we'll talk about the degrees and the coefficients. So f of x approaches what as x goes to infinity? And f of x approaches what as x goes to negative infinity. Okay, so as our x goes to positive infinity here, where's our end of our graph going? Negative, so we'll fill this in with a negative infinity. And then as x is going to negative infinity, so the left-hand side of the graph, where are we going? Positive infinity. Okay, so that's how we describe end behavior. That format is the standard way how it's described. So now, we also know some things about the leading coefficient of our graph and some things about the degree. Okay? So these first 2 graphs on this left-hand side, this kind of look like a quadratic. What's the degree of a quadratic? What's our highest exponent of a quadratic? So quadratic equation, what's the exponent? Yeah, curves. So what's the exponent for the equations? Squared. Like an x squared is always the highest exponent. 2. Is that an even number or an odd number? It's an even number. So when we have both of our ends ending in the same direction, so here they're both ending up, here they're both ending down, this is an even function. So this has an even degree. Okay? So when our ends of our graph are both up or both down, it's an even degree function. When they're ending in opposite directions, like our second 2 graphs over here, when we end in opposite functions, it ends up being an odd degree. So these 2 functions on the right-hand side might have a highest degree of 3, or of 5, or of 7. But if the ends end in opposite directions, it's always odd. It would still be even. Yep. And then the last thing we can also tell just by looking at these graphs is the leading coefficient and what the leading coefficient looks like. So these top two graphs have something in common, and these bottom two graphs have something in common. So let's look at the quadratics and think about the quadratic ones here, or the ones that look like quadratics. When we're opening up, was our a value, was it positive or negative? Positive. That was our leading coefficient for our quadratic, was that value that a was. So when we were positive, we opened up, and we were negative, we opened down. We really are just going to focus on the right-hand side of the graph to determine this. If the right-hand side of the graph is going towards infinity, the leading coefficient is a positive number. If the left-hand side of the graph is going towards negative infinity or is going down, the leading coefficient is a negative number. Okay, so this just gives you an idea of what the graph should look like and what type of graphs you have if I give you some to look at.
So the right side goes down and it's negative?
Yep, when the right side goes down, it's negative.
But you
Only look at the right side.
What if, like, they don't both come down? What if, like, you never compare ones that don't have the same LC? Like, you're not going to have us compare ones that, like, say that one's right side is going down, the other one's right side is going up.
That wouldn't be the same graph then.
Okay.
You're just going to have one graph to look at. So here's two graphs we're going to look at. For each graph, we're going to describe the end behavior, determine if it represents an odd or an even degree polynomial, determine if the leading coefficient is positive or negative, and then state the number of real zeros. We'll talk about real zeros after we've done the other three things. These are just sketches of graphs, so they really don't have to be exact whatsoever. So this kind of looks like a curvy M, maybe. All right, so we're going to start off with naming the end behavior here. So f of x approaches what as x goes to infinity? And f of x approaches what as x goes to negative infinity? So as x goes to infinity, so on the right-hand side of this graph, which way are we heading? Negative infinity, because we're heading down. As x goes to negative infinity, so on the left-hand side of this graph, where is our f of x going? Negative infinity, it's going down. All right, that okay for end behavior? Would this one be an even or an odd degree? This would be even, and why would this one be an even degree? Yep, they're both going the same way, see they're both going down. The leading coefficient here, would it be a positive number or a negative number? This would be a negative number. The right-hand side is going down, so the leading coefficient is negative. And then the last part of this, the number of real zeros. When we did quadratics, we talked about we had real zeros every time we crossed the x-axis. That's the same case here. The real zeros, these happen every time you cross the x-axis. So here, we cross the x-axis in two locations. So we have two real zeros.
So it's only where it crosses the x?
Yep, only where it crosses the x. And remember, real just means they are actually real numbers. They're not imaginary, essentially.
Oh, that makes sense because that's what it would be is 0 when it's crossing x.
Exactly. Yep. Is that okay? Make sense? Okay, we'll look at one more. So this next graph here. So, first I have to talk about end behavior. So f of x approaches what as x goes to infinity? And f of x approaches what as x goes to negative infinity? Okay, so on the right-hand side, where are we going? There are names for it, but it's not really applicable to this right now. So f of x approaches which way as we are on the right-hand side? Positive infinity. And on the left-hand side, we're going to, negative infinity. Yeah, is this an even or an odd function?
Odd.
This is odd because if we look at our two ends, they're going off in opposite directions. So this would be an odd function. The leading coefficient here is going to be positive. Yep, and how do we know it's positive?
It's the right one goes up.
Yep, the right side here is going up. And then how many real zeros would we have? We have this one real zero right here where it crosses. Is that okay?